Hello everyone, my name is Michael Siminovich and I'm a professor at the University of California, Davis in the United States. I'm also the holder of the Rosenfeld Chair in Energy Efficiency and I'm director of the Lighting Technology Center. Today I'm going to be talking about circadian home design, and it represents a body of research and endeavor that we've been pursuing at the university for the last number of years. Today, I'm going to talk about circadian design, and I've broken this into 4 different sections. The first section is going to be the basic science of circadian, where I'm going to review the basic science, the foundation, and some of the critical issues associated with circadian biology. And at the university, we built the first circadian home that embodies the main principles of circadian design, and I'm going to talk about that. The third section, I'm going to talk about dark adaptation and how circadian design and dark adaptation work together in terms of providing a wellness home environment. The last section is going to be recommendations that you can do in your own home or your own residence to adopt or to modify or to include some of these basic concepts in circadian design. So first I'm going to talk about some of the basic principles of circadian lighting and circadian biology, just as a foundation for the rest of the presentation. Circadian, the actual word, derives from Latin and refers to about the day. And it really refers to the fact that the basic lighting conditions in our natural environment change throughout the day. And so the whole concept of circadian refers to the fact that lighting characteristics are highly variable throughout the day. So we call this circadian. So what I'm showing here is basically a color signature of sunlight or of daylight. And daylight is a very rich color spectrum. It produces a very broad color all the way from blue to far infrared. And when we think about daylight distribution or the spectral color characteristics of daylight, we think of this very continuous kind of color. However, daylight is very dynamic and it changes its spectral content throughout the day. And this is really the basis of circadian design. And so in terms of our own biology, we've evolved under this very dynamic light source. And the very early morning and the very late evening, we have a very reddish amber spectrum where the color is very warm. And our biology is basically very much wired to seeing this. However, in the middle of the day, it's very white or very blue or a very cool kind of color distribution. So our evolution has really evolved with the concept that we go from a very reddish amber to a very white, bluish light during midday. And then, of course, as evening comes, the sun starts setting, it reverses, and now we come back to a very rich red, amberish kind of spectrum. So our biology has evolved very closely to this kind of dynamic characteristic of daylight. So if we look at the color signatures like I began with, if you actually look at the variability, this slide shows that daylight can have many different color characteristics. It can be, very rich in the blue end of the spectrum, and contrary, it can be very rich in the red amber spectrum, depending upon the time of day. So this highly variable daylight characteristic is something that our biology is very closely wired to. And this is referred to circadian. And so when you look at this and you summarize what the characteristics of our diurnal variations in daylight, it really looks like something like this, where it goes through this diurnal or daily cycle where it migrates from a very warm red, amber, to a very white, bluish, and it goes through this kind of cycle. We are happiest as a species in terms of our biology when we have this kind of lighting characteristic. And there's a lot of research that supports this, that our melatonin, our foundation hormones, are very much tied to the spectral distribution that you see in this very nice graphic. And so you can reduce this graphic where you actually look at melatonin. And melatonin is very much driven by the spectral distribution and the intensity of light throughout the day. And so if you look at very early in the morning, our melatonin starts decreasing with the available light. Light washes out the melatonin. It goes to a minimum throughout the day. And then as the sun starts setting, it starts increasing and building towards the evening hours. And now we have a very high level of melatonin, and we go to sleep. And so this is very much supported by the dynamic changes in daylight or lighting conditions. At nighttime, no light, no blue, very high melatonin. During the day, lots of light, we reduce the melatonin. And so in lighting design and architecture, and how we light our homes and buildings, there's basically traditionally two pathways. And one is a visual pathway where we light for movement, for visibility, for color recognition. And this is kind of the normal expectation. You turn on the lights and you can make visual decisions in terms of egress, looking at colors. But there's a very important secondary pathway called the biological pathway. And this refers to how light impacts our melatonin. And so when we have a lot of light, we have very reduced melatonin. When we have very little light, melatonin builds up in our system. So this is called the biological pathway. Modern light sources, the solid state lighting technologies that we put into our home, can create some interferences with melatonin production. And so the basic anatomy of an LED is that there's a small semiconductor chip, and it makes a very concentrated blue light that then activates a phosphor that then makes white light. And this is a very basic principle in terms of how we put light in today's buildings. And these are called traditionally blue pump phosphors. They make blue light that then re-emits into the visible spectrum. The issue with this is that if you look at the color signature for a typical LED, there's a strong component in the blue spectrum and then a continuous spectrum that goes off into red, and this is the white portion. When we see this kind of blue band here, we interpret this as white light, but we're giving a very strong stimulus in the blue end of the spectrum. And this blue component, around 460, 480 nanometers, happens to coincide with our circadian sensitivity. And what this means is that when we see this kind of light, it suppresses melatonin. And this is not a good thing at night. It's a good thing during the day, but it's not good at night. The American Medical Association in the United States a number of years ago came out with some very important directives that said, actually, light at night, in all probability, is not good for us. And the rationale there is that this blue light that's inside the LED is suppressing melatonin. And so the hours that we watch television or we work on our computers or we have a lot of light in the home, this is actually not good for us. And it's suppressing melatonin and interferes with sleep. So the American Medical Association said we need to be very careful about how we introduce light into spaces. So again, if I look at color signatures, it turns out that light in the 460, 480 nanometers is very effective at suppressing melatonin. And however, light that's yellow, amber, red does not suppress melatonin. And so these different characteristics of light need to be used strategically in the lighting of our home in order to optimize circadian design and keep us as healthful individuals in the home. And there's things that you can do in the home to actually create this. This is actually a graph showing melatonin suppression, and what the scientists did in this study was that they looked at a number of different light intensities in the home, and they looked at relative levels of melatonin suppression. And essentially what we're showing here is that low levels of light can actually be quite suppressive. The green box that I'm showing in here represents a typical living room, And the boundary condition that I'm outlining here shows that melatonin can be anywhere from 75 to 25% suppressed just with normal lighting that we see in the home at night. So the way we light our homes is not good in terms of melatonin suppression. This graph is actually from one of my colleagues. And what they did here is they looked at the lighting characteristics in terms of light intensity for the ancient hunter-gatherer versus modern and industrial culture, the kind of culture that we live in now. And so if you look at the blue line, if you look at throughout the day, is that early in the morning, we get very bright light. Humans were subject to very high light levels, and then it depreciated throughout the day. A sunset, it went to very low light levels. And so our ancestors saw very high light levels during the day and very low light levels, if any light at all, at night. And this is basically the kind of perfect geometry that you want to support circadian wellness. And so our ancestors that were hunter-gatherers actually lived under very excellent circadian lighting conditions. However, if you look at the modern culture today, most of us are inside. We're inside schools or we're inside work environments where the light level is considerably reduced. We're not getting enough light to suppress melatonin. And in the evening, we're sitting and watching television, or we're under high light conditions, working on our computers or our cell phones. We have much higher light levels than our ancestors saw. So it's actually a very incorrect, very disruptive circadian lighting geometry. And I've shown some pictures here to kind of illustrate this. If you look at our ancestors, our hunter-gatherers on the top picture, these folks were outside all day, and they were subjected to very high light levels. They had ideal kinds of lighting conditions to suppress melatonin. You look at the bottom picture, it's sort of a typical office, very low lighting conditions, nowhere near the kinds of lighting that we have outside. Not good. And then if you look at evening hours, our ancestors, this was the kind of light that they experienced. They saw basically starlight, very low-level light. But our typical living rooms are very bright. So this kind of shows you on a sort of a pictorial what's going on.